In this section, we're going to do some application problems that involve trig functions. The good news is there's no new applications. Like the types of applications are all the same. They're going to be optimization problems or related rates or maybe curvilinear motion or something. The same types of applications we learned in Chapter 3. They're just going to be scenarios that involve trigonometric functions. So we'll start with a related rates problem. So a rocket taking off vertically, a distance of 6,500 feet from an observer. So imagine there's some observer over here. And it says that when the angle of elevation is 38.4 degrees, it is changing at the rate of 5 degrees per second. This it is the angle of elevation. So it is changing, theta is changing at the rate of 5 degrees per second. How fast is the rocket ascending? So they've given us one rate. We know what the rate of the angle is changing at a particular point when the angle is 38.4 degrees. And then they ask us about another rate. How fast is the rocket ascending? That's how fast x is changing. So you might have noticed, I talk a lot about how in these applications we will need to be in radians. They've given us these measurements in degrees. And so we should actually convert these to radians, and one thing we have to keep in mind is that radians as a unit for measuring angles is innately tied to an idea of measuring distance. It is not a distance absolutely, like it's not, radians are considered dimensionless. However, when we measure an angle, I'm going to go back to the unit circle here. So this is the point 1, 0. And this is the point 0, 1, and so on, right? So if I'm just going to draw an angle, I'm just putting it in the first quadrant for fun, but it's true regardless. So let's say I have this angle theta. If theta is measured in radians, then the measure of theta is the arc length, is the length of the arc that it cuts out on the unit circle. So there is a connection to the idea of measuring distance, measuring length with measuring an angle in radians. And that's why, especially for these problems where we're comparing, some distance, in this case x, how high the rocket is, with a measure of an angle, we really want to be in radian mode. So I'm going to change the 5 degrees per second to radians per second. 180 degrees is equal to pi radians. You could put this as do it out on the calculator and write it as a decimal. I am going to just reduce. So 5 goes into 180 36 times. So this is pi over 36 radians per second. And then the other measure they gave us was this measure at 38.4 degrees. So I'm just going to convert that. And that angle was already given in as a decimal, so I'm just going to approximate this. You get 0.6702. So now let's put this together. They said when the angle of elevation is 38.4 degrees, it's changing at 5 degrees per second. That means that what we know is that d theta dt, when theta is 0.6702, is equal to pi over 36. And what we want, how fast is the rocket ascending? We want dx dt. Okay, so we've kind of set this up. We know the derivative that we know. We've identified the derivative we want. What we need is an equation that we can differentiate with respect to time. So looking at the right triangle, when you see right triangles, there's two things that might leap to mind. One is Pythagoras and the other is SOHCAHTOA. And since we need our equation to involve theta, we've got to look to SOHCAHTOA. So thinking about what my options are, and knowing that I want it to involve theta, this side x, and this fixed side. You know, they talk about, I didn't talk much about the fact that this person is 6,500 feet from the observer, but that means that that side of the triangle is not changing, and if I can use a fixed quantity in my equation, that's nice. It makes things easier. I could get an expression for, you know, the hypotenuse and decide to use another function, but it's much easier if we can involve the fixed side. And so when we do that, that means I'm going to use tangent, because that's opposite over adjacent. So we find that tan theta is equal to x over 6,500. Which I'm going to rewrite real quick as 1 over 6,500 times x. Now I'm going to differentiate both sides. Secant squared theta times d theta dt is equal to 1 over 6,500 times dx dt. We want to find dx dt. What I'm going to do, because we know d theta dt for a given value, I am going to just solve this for d theta dt first, and then plug in our known value, and then we'll be able to evaluate dx dt. So I'm going to, in order to solve for d theta dt, we would divide by secant squared. Now that's the same as multiplying by cosine squared, because these are reciprocals. So d theta dt is cosine squared theta over 6,500 times dx dt. Now we know the value of d theta dt at theta equals 0.6702 radians. And we know that at that point d theta dt is pi over 36. And since we know d theta dt is a function, then pi over 36 must be equal to cosine squared 0.6702 over 6,500 times dx dt. And we can take this equation, solve this equation. Just going to multiply both sides by the reciprocal of that fraction, the cosine squared over 6,500. So then dx dt is equal to pi over 36 times 6,500 over cosine squared 0.6702. And let's see what we get. So 6,500 pi up top divided by, now when I am, I've got my denominators 36 times cosine squared. I have to make sure when I plug this in the calculator that I put the whole denominator in parentheses. Square the cosine, so I close the cosine function, then I square it. Now I'm closing the parentheses on the denominator, and I get 923.56. Now units for this are going to be units of x over units of time. So the x units, that was distance, and our distance units here I could tell are in feet, so it'll be feet per second. All right, before I do another one, I just want to point out that I went through this and we solved this problem using the tangent function. Once you pick a function, you have another option for how to proceed. So if I took this, I could also proceed this way to say, well, that means that theta is arctan of x over 6500. And then differentiate both sides with respect to t. And you'll still get the same correct answer. Really, sometimes one method might require an extra step, but they're usually a comparable amount of work. So whichever method you feel comfortable with is the one I would choose. Okay, we're going to do another one. A particle is moving so that its x and y coordinates are given by x equals cosine 2t, y equals sine 2t. So we have a pair of parametric equations, and we're going to find the magnitude and direction of its velocity when t is equal to pi over 8. Okay, so this is a vector problem, right? Curvilinear motion. So if x is equal to cosine 2t, we're going to differentiate. We're going to find dx dt. This is negative 2 sine 2t. Right, the derivative of cosine is negative sine. We need that factor of 2. That comes from the chain rule. And now we want, let's see, we found dx dt so that we could get the x component. So vx is going to be what we get when we plug in t equals pi over 8. So that's 2 times sine of pi over 4. Sine of pi over 4, you could use, decimals. You could plug this in the calculator and use decimals. Make sure your calculator's in radian mode. You could also use the unit circle. At pi over 4, we can see here that the y coordinate is the square root of 2 over 2, so that means sine is equal to the square root of 2 over 2. These will reduce, and we get negative root 2 for Vx. I'm going to do the same thing with the y function. Y is equal to sine 2t. So dy dt is 2 times cosine 2t. The derivative of sine is cosine, and we get that factor of 2. It comes from using the chain rule. This means now Vy is 2 times cosine of 2 times pi over 8, or 2 cosine pi over 4. And again, looking at the unit circle, at pi over 4, that's where sine and cosine are equal. So they're both root 2 over 2. Cancel those 2's. So Vy is the square root of 2. Now looking at these two components here, we can tell that this is going to be in quadrant 2. Negative x, positive y. This is quadrant 2. That's going to affect our angle when we find it. The magnitude, we're going to use Pythagoras for. So the square root of what, 2 plus 2, or the square root of 4, which is of course 2. So there's our magnitude. For the direction, now we've been using a lot of stuff in radians. With vectors, it's still pretty customary to give the direction using degrees. If you choose radians, that's totally fine. Chances are pretty good if you check any answers in the back, in the exercises. They might be using degrees. I'm going to go ahead and put my calculator in degree mode to get the direction. It's in quadrant 2, so that means theta is 180 minus arctan of root 2 over root 2. Remember, we always plug in positives to the arctan when we're finding the angle of a vector. Root 2 over root 2 is just 1. So this gives us 135 degrees. And that means that our vector is 2. Let's see, they didn't give us any units in this problem, so our answer will not have units. The magnitude of 2 at an angle of 135 degrees. Okay, let's do one more. Here we've got logs with a circular cross-section 4 feet in diameter are cut in half lengthwise. So after they're cut in half, it looks like right here we're looking at the butt end of that log. We're going to find the largest rectangular cross-sectional area that can be cut from one of the halves. So it's not necessary, I mean it's possible to solve this problem without using trig functions, but there's sort of a convenience to using trig functions here. At first, our equation isn't going to look like it uses trig functions at all. So just to note, so y is this vertical distance, x is just this distance here. So if I'm trying to maximize the area of this rectangle, the lengthwise dimension is 2 times x. And so we want to maximize area, which is length times width, or in this case, 2x times y. Now that's not, there's no trig functions there, but we can make trig functions out of this. So we know the measurement from the center of the bottom out to the edge because the circular cross-section was 4 feet in diameter, which means that this is a radius, that diagonal. So that's 2 feet. And let's say we pick, if we draw this out as they've indicated from the bottom out to where it intersects this circle, we'll call this angle theta. Now use this right triangle. We're going to make some trig functions. If I use the sine function, we find that sine theta, opposite over hypotenuse, is y over 2. And if you multiply both sides by 2, we find that y is equal to 2 sine theta. Similarly, if I use the cosine function, cosine theta is adjacent over hypotenuse, so that's x over 2, and that means that x is 2 cosine theta. So now I'm just going to replace x and y in the equation up here for area with these expressions that we found. So 2 times 2 cosine theta times 2 sine theta. So this is, now I could write that as 8 times cosine times sine, but here's what I'm going to do. I'm going to write it as 4 times and then 2 sine theta cosine theta. Here's the thing. As it looks right now, it appears like we have a product. I mean, we do have a product, and we could find the derivative using the product rule. However, if you use the double angle formula here, this is equal to sine of 2 theta, and then the derivative just becomes easier. So we have 4 sine 2 theta. And we haven't done any, this isn't calculus yet. This is still just what the area is as a function of theta. Now if we're looking to maximize, that means we need critical values. We're going to find the derivative, set the derivative equal to 0 to find those critical values. So we have 4 cosine 2 theta, derivative of sine is cosine, and then chain rule says we're going to multiply by 2, so we get 8 cosine 2 theta. That is A prime. And if we want to set this equal to 0, we want to find where this is equal to 0, well, that only happens, like 8 is never equal to 0, so 8 times cosine 2 theta is only 0 when cosine 2 theta is 0. So where is cosine equal to 0? Well, if we look at the unit circle, cosine is the x-coordinate, so cosine is 0 at pi over 2 at the top of the circle and at 3 pi over 2 at the bottom of the circle. Now I just want to talk a little bit about the range of values that we're considering for theta. Up here, theta clearly can only go from 0 to pi, right? From 0 to 180, one half revolution. Our function has 2 theta as an argument, so if theta can go from 0 to pi, theta has to be allowed to go one full go around the circle. So the values of theta that this produces, of 2 thetas pi over 2 and 3 pi over 2, this produces theta equals pi over 4 and 3 pi over 4. And, 3 pi over 4 is just the mirror image from pi over 4 over in the second quadrant. So these 2 angles actually produce the same cross section. So now we want to just make sure that we found a maximum. Let's find the second derivative. The derivative cosine is negative sine, so we have negative 8 sine 2 theta times 2, so negative 16 sine of 2 theta. And if we plug in pi over 4, negative 16 sine of 2 times pi over 4 is pi over 2. That's negative 16. The fact that the 16 is not that important, so that this is negative, so that means it's concave down, and that means that pi over 4 gives a max. So now let's go ahead and find the maximum area. Find that maximum area, we get 4 times sine of 2 times pi over 4, 4 times sine of pi over 2, which gives us 4. And our units are in feet, so the area is in square feet.